Okay, today we're going to talk about how to balance chemical equations, show you some tips and tricks, and some examples. Before we start, I just want to point out that the steps I'm going to show you initially are meant to just guide you a little bit while you're first learning how to balance equations. They're not meant to be used permanently because most people are going to pick up on the intuition behind how to solve these things without the individual steps, but they're useful at the very beginning. So giving sort of a brief preview, the idea here is to have each one of these atoms have the same number on each side. We see with this simple equation, they are in good shape with the sodium, but not so much with the chlorine, forming something that most people are fairly familiar with on a day-to-day basis. Anyway, so our problem here is we've got to get these chlorines over here to be the same as these chlorines over here. And one of the steps I'm going to show you says something about changing the coefficients. And I want to point out the coefficients are the big numbers that go right here that I'm going to show you in just a minute. They are not over here, the subscripts. It is sort of a cardinal rule that you do not mess with the subscripts in balancing equations. If nothing else, it changes it into something else. For one, there's no such thing as NaCl2. And if there were, it would be something different than an ACl. This is one of the reasons I use this other equation. And the equation is hydrogen gas plus oxygen gas explosively leads to water. And we've got the same situation here where we've got the same number of hydrogens, but our oxygens are different. And one thing we can't do is to just add a little 2 down there to make everything all great, and it would be great on paper, except for the fact that H2O2 and H2O are not the same thing. H2O is water, and H2O2 is hydrogen peroxide, and most people are familiar enough with things to know that they're not the same thing, and you can't drink hydrogen peroxide, for example. So instead of messing with the subscripts, this is the reason that it's doesn't work. We have to change the coefficients out front, and so this is just a little preface to note the difference between changing the subscripts and changing the coefficients and why that's so important. An example using this same equation. So again, count the atoms on each side. We already established the sodiums are fine, the chlorines are not. And since we can't mess with the subscripts here, we have to change the coefficients. Change the coefficient of one of the imbalanced reactants or products so it matches the numbers of atoms on each side. Now, as is often the case, whenever you mess with one atom and fix that, you are inadvertently messing with another one. So you always want to count the numbers of atoms again, and if they're the same, you're done. But in this case, you're not, because the sodium has been messed up. So we have to go back and repeat steps 2 and 3 until the equation is balanced. And fortunately, this time, we only have to fix that sodium, and then we are in fact done. So these are the basic steps that you're going to want to use, and they'll work on just about any equation. All right, so another example is the one that I showed just a minute or two ago, hydrogen burning in air and oxygen and forming water. And it's sort of a similar thing. We can't mess with the subscripts here to fix everything. So what we do is we change the coefficient. We add a 2 there. And once again, we fixed the oxygen, but we've messed up the hydrogen. So we come back, we add a 2 over here, and we double check, and everything looks good. We count again, and everything looks good, and we're done with this one. Unfortunately, not all these are quite this simple, but these are good to start with. All right, here's another one. This is iron reacting with oxygen to form iron oxide. Now this is a little trick that will help you out sometimes in certain situations. If you notice that there are an odd number of atoms on one side and an even number of atoms on the other side, probably everybody would agree that you're never ever going to have it balanced if you have an odd number on one side and an even number on the other side. So the little trick is basically just to double it. It's just to put a 2 out front. Now, more often than not, that doesn't fix everything immediately, but it gets you on the way to fixing things a lot more rapidly. So we put a 2 out front. You notice it doesn't fix everything. We've got 6 oxygens here, but at least 6 is an even number. We come back over here and we can add a 3, and now we actually have in fact fixed the oxygens. And in fact, the only thing that's not balanced now is the iron. So we've got 4 irons here. You can just put a 4 right there, and then we are in fact done. Now, one of the things that used to fluster me a little bit is that being a little bit uncertain where to start. And then if you start in a different place than what the teacher or the professor is showing you on the board, is that going to, cause you to get it wrong? If you'll look at another copy of this here, we'll go through another example. If we go through and we think about a rule about the even and odd numbered atoms, say, oh, hey, this is odd and over here is even. Let's double that. And then go on from there. Well, we still obviously have to go back and fix our oxygen over here, so we'll do that. And then we've got 6 oxygens here, so we want to make a total of 6 oxygen atoms here. And everything's all fine and wonderful except that our iron is wrong now. But that's not a big tragedy. This basically all you have to do is erase it or scratch it out and just change it. I had a big aversion to changing the coefficients when I was balancing, but if you notice, we get exactly the same answer. So just wanted to point that out. Another one we have here, it's a little bit more complicated. This is one where I probably recommend making a little table at the bottom to keep up with everything so you don't accidentally write something down twice or forget to write something down. But one thing I want to point out is that you'll notice that on both sides of the equation, we've got sulfates. We've got SO4. And those sulfates don't change any before the reaction starts and after the reaction ends. So you can treat those sulfates as if they're one big atom. They're not really, obviously, but you can treat them as one unit so that you don't have to keep up with the individual sulfurs and the individual oxygens. And that will be the case with any polyatomic ion that you're going to run across, some that you've certainly seen before, sulfate, sulfite, nitrate, nitrite, things like that, hydroxide. So anyway, that saves us a little bit of time. So down here on the bottom, I've got a table that I made ahead of time just to speed things along. And where to start is sometimes I used to get flustered over. You'll notice over here you've got an odd number of sulfates, and then sometimes people will make a mistake and try to double something over here, but you'll notice we also have an odd number of sulfates. So what we're going to want to do is just to fix the number over here, just add a 3 there, and now we've actually fixed our sulfates, but you see we've also changed our hydrogens. So we come over here to look at our hydrogens. We got 6 hydrogens on this side. We're going to want to put a 3 there to make a total of 6 there. We adjust it right there on the bottom in the chart. And our aluminum is really the only thing left, and we've got 2 over here. We had 1 over here, so we fixed that. And we adjust our table, and we'll look down at our table, and it tells us, hey, we're done. So that's a little bit more work than some of the earlier ones, but if you have a method to doing all this, you'll turn out fine. All right, here's another one. And this one's going to be a little bit more simple. Silicon dioxide plus carbon, and yielding silicon carbide and carbon monoxide. You'll notice again, we've got an odd number of oxygens. We've got an even number of oxygens here. So we're going to want to put a 2 there. And here is a place where sometimes people will make a mistake. They'll say, okay, well, I've got to fix my carbons, and there's 2 carbons here, and so I'll put a 2. But the only problem is there's 2 carbons here, but there's also a carbon there. So there's a total of 3 carbons on this side and not 2. And so you always want to check and make sure that none of your elements are kind of spread out over different compounds like that. So if you put a 3 there, if you miss that little pothole there, if you miss that little trap, if you put a 3 there, then you're done. You finished, and everything's all perfectly fine. But you got to be careful for little things like that will pop up every now and then. All right. Got another one, calcium hydroxide and aluminum sulfate, and we have both sulfate and hydroxide that show up on both sides. So that saves us a ton of work. Got our little table down here at the bottom that I've made ahead of time. The first thing we're going to notice is that our aluminums are pretty easy to fix. We just put a 2 right there, and then we see what type of effect that has on our hydroxides, you see that changes our hydroxides. Our hydroxides, we've got a total of 6 now. So we're going to want to come over here and fix that. So now we have a total of 6 hydroxides. We've noticeably we've messed up our calciums too. So we have to come back over here and fix our calciums. And now we've got that fixed right there. And now we've got 3 and 3, 6 and 6, 2 and 2, and then 3 and 3 again. We're done. So that's the utility of making a little table like that when you've got a very complicated equation. All right, just a few more. Calcium hydroxide and potassium sulfate. Again, we've got a situation with sulfate on both sides, hydroxide on both sides. We'll make our table down here. One of the first things that we notice, for example, this potassium is kind of sitting right here in front of us, front and center. There's 2 there. There's only 1 there, so that's a convenient place to fix that. We also have got our hydroxide. It changes our hydroxide, obviously. There was 2 over here. There used to be 1. Now there's 2. And now suddenly, if you look down at our table, everything's done. That surprises beginning students sometimes. They'll see a long, complicated looking equation like that and expect to have to spend an hour on it. And sometimes you can fix it in just one adjustment there. So I wanted to throw in an example like that. Okay, the last example is a reaction of ammonia and iodine. And you see here sort of in the center of the equation, the most obvious place it looks like to start is with the iodine, because you've got 2 on one side and 6 on the other. So the most obvious thing that we can do is just put a 3 there. Then we probably want to work on our nitrogen, because we've got an odd number on the left hand and even number on the right hand. So we can fix that as well. But we notice that we've also messed up our hydrogen. So we've got 6 hydrogens on the left hand side, only 2 on the right, but that's pretty easily fixable. And it looks like we're done with this as well. Just to sort of parenthetically, there's not really a hard and fast rule that I use of when to make a table and when not, but this is probably about the border, cutoff. So we could have made a table with this, but it worked out pretty well as it was. So this is our final example. And that is the end for now.